Hello, and welcome to Agrosive Physics. Today is day 23, and what I'd like to do today is talk about the methodology we're going to use in order to solve projectile motion problems. But let's revisit the question we had a few days ago. Which ball will land first? If I throw a ball horizontally and I drop one at the same time, which one will hit the ground first? And we discussed the fact that they both will land simultaneously because we're able to treat the x and y directions as independent. Perpendicular vectors are independent. Well, what I'd like to do today is show you a visual representation of that and hopefully prove to you once and for all that this is true. So if we look at this strobe light photo, we'll see that both balls hit the ground simultaneously. Now, how do we get a strobe light photo? Well, what basically we do is we leave a picture exposed, a camera exposed with the shutter open the entire time. And we have a strobe light flash at a specific rate of frequency. Now, that means that every time the strobe light is on, light is reflecting from the object, in this case, two balls, and they are entering the camera. Well, as the balls move, we're only seeing them when the light is flashing. And if we have a consistent flash rate, we're going to see the balls in different intervals of time, each meaning a certain amount of time has passed. So in this case, we have the red ball moving vertically, and we have the yellow ball moving horizontally forward. It's just being pushed forward at the same time. Well, you'll see that over the course of time, they both are at the same height. Now, there could be some discrepancy because of friction, but remember that as we look at this photo, they're both at the bottom of the screen at the same spot. So they're going to land simultaneously. You may say a bullet's going to travel a lot farther. Sure, a bullet travels farther. However, it's still acting vertically because of gravity. It's still accelerating at the ground at a rate of 9.8 meters per second squared. The only time that would cause trouble is if we shot something so fast that the ground actually curved away as it's falling. If the curvature of the Earth were taken into account and the object were moving fast enough, that would matter. In fact, that is what happens when we orbit objects. And what we'll discuss is when we discussed that with weightlessness earlier, we discussed the fact that as an object is falling towards the Earth is actually curving out of the way. If it curves, let's say it falls a meter, and the Earth curves a meter, it will always be at the same height. Any object that's in orbit is traveling fast enough to overcome the curve of the Earth. So this could be an issue when we're dealing with objects traveling at a super high rate of speed. But for our purposes right now, even a bullet doesn't travel fast enough to do that. Now, from the strobe light, if we look at the motion in the sideways direction for the yellow ball, we will see that they are equidistant. They are the same distance apart. Now that means we have constant velocity. The way I remember it, if the dots are equidistant, the motion is consistent. So we have constant velocity in the sideways direction. Now, why would we have no sideways motion? Well, gravity doesn't act sideways. It only acts vertically. And we're going to treat the x direction as different from the y direction. Now, if we look at the y direction, we'll see that the dots are getting farther apart, which means we have accelerated motion. So, if the dots are equidistant, the motion is consistent. If the dots are ever changing, the motion is accelerating. Maybe not as good a mnemonic, maybe not as good in terms of poetic license, but equidistant, consistent, ever changing, accelerating. So if the dots get farther apart, you're accelerating. If they're farther apart, you're speeding up. What do you think is going to happen if the dots are getting closer together? You got it. They're slowing down. So just looking at the dot pattern from an object in motion, you can determine whether or not it's accelerating or moving at a constant rate. There's a device called a ticker tape machine that physicists have used throughout physics courses to represent the motion of objects. With higher technology, we use motion sensors, and it does the work for us. It graphs it, directly in real time. But the original physics courses, the physics course I took when I was in high school back in 1992, we were using ticker tape machines to represent motion. So we'd have objects connected to a roll of paper. It was carbon paper. And we would drop objects down ramps or drop objects vertically. And we had what we called a spark timer. And the spark timer moved basically a piston at a rate of 60 hertz because the rate of electricity is at 60 hertz in our country. If we did this experiment in Europe, it would be 50 hertz. But when it oscillated 60 times a second, kind of like maybe an old telegraph machine, but really fast, what would happen is it would make a dot on the paper 60 times every second. Well, as we moved the object forward, it would spread the dots out. Constant rate, the dots would be equidistant. Acceleration, the dots would get farther apart or closer together. We were able to measure how far apart they were and actually make a graph by hand. And in class, I think that's something we're going to explore. But for now, remember that equidistant dots, consistent, changing dots, accelerating. A little mnemonic to remember. But in this case, although the balls are traveling at the same height each time, they're getting farther apart, and it's going to represent accelerated motion. Now, why would the objects accelerate in the vertical direction? You got it. Acceleration of gravity. If we were to calculate that value, it should be 9.8 meters per second squared. We could make a graph of displacement versus time, figure out the velocity of different points, and we should be able to determine the acceleration of gravity from this data. Unfortunately, we don't know the frame rate. Now, if this were a video, it would probably be 30 frames per second. If this were a spark timer, it would be 60 hertz or 60 times per second. So we would have time values. But for this picture, we don't have the time values. We actually don't have the distance values as well. I don't know what those lines represent in terms of distances. We could make up a number, but then we wouldn't be able to determine if it's the acceleration of gravity or not. Now, that being said, what we know is that perpendicular vectors are independent. So the x direction and the y direction can be treated as two separate problems. The x direction is constant velocity, and the y direction is accelerated. And if we have uniform motion in each direction, we can use the big five equations to calculate whatever it is we want to find in either of the two directions. But it's important to realize that there's one variable that's constant for both directions, and that's the time. And that's the variable that's going to allow us to bridge the gap between the x and the y directions. That's the variable that is going to be the key to solving projectile motion problems. T is the key. Now, that being said, if we treat each problem as a separate entity and we combine them together to find the displacement in the y or the time for either one, we're going to be able to solve more complex problems. So for today, I just wanted to discuss the qualitative concepts of that. We can solve these problems because they're perpendicular. I wanted to give you a visual representation so you can see that representation, the fact that the x and the y directions are the same in this case. And tomorrow what we'll do is we'll look at solving actual problems using our givens lists and solving for actual variables. But for today, if we treat the x and the y directions as two separate problems, we're going to be able to solve any two-dimensional projectile motion problem.